Recording in progress.
Welcome to lecture 1, week 4. Let me go and get some notes at once. Right there. Let me see. I'll go again. I'll share with you. And then I'll go to OneNote at once. Right there. And then that is us. And then I'll go to at once to here. Page. And this is lecture 1, week 4. Discrete Math, Spring 2025. Just a pure formality. Let me check that the cameras are on. It's just a pure formality, really fast. Right there. I'm taking a look at the attendance right now, but I'll take a look at the attendance later in Zoom. Thank you. Okay, so at once, I'll go to OneNote. Any questions from chapter 3? Our last section is 3.3 and is multiple quantifiers. Right, that was the last thing that we did. Let me go right away to the calendar at once. Let me see, that is us. And I'll run to the syllabus calendar. So there. I'll open the syllabus and I'll download the syllabus and I'll scroll to the calendar. Week 2, there we're on week 4, there, so there, week 4. Week 5, so our test is the 20th. Let me go and bring this. So those are going to be the topics right there. So I'll bring it to our notes. There. Control V. So our next topic is not going to be now, whatever I'm going to talk right now is not going to be on the exam because I'm going to start talking about section 4.1. But first, do you have any questions from, we're going up to section 3.3, so we are not doing section 3.4. We are not doing arguments with quantifiers. We're not doing arguments with quantifiers. So we'll stop at 3.3. Okay, let me see. Section 4.1, but if you think of a question, a pleasure to answer. I put a new, let me admit to students right there. I put a new immediate right there. Let me see. If I go to grade scope, I put a new immediate that is dealing with section 3.2 and 3.3. Right there, let me see. Did I go to the right there? There is the immediate, and it's 3 problems. 2 problems from 3.2 and 1 problem from 3.3. Right there. So there, let me go right away to here. Section 4.4. So chapter 4. Chapter 4 right there. So that's it. We have all the logic that we need to be able to start doing proofs. So from chapters 1, 2, and 3, we have all the logic that we need. So section 4.1 we'll start some simple proofs right there. Section 4.1. So we need a definition. If we're going to start writing some proofs, we need a definition. So I'll give you the definition of an even integer. I'll give you the definition of an even integer. Here it comes. N is even. N is an even integer. If and only if. I can say also, to be less precise, I can say means. But it's a definition, if and only if. And it's equal to 2k for some k in Z. Z is the set of integers right there. So Z is minus 3, minus 2, minus 1, 0, and so on. Right there. So that's that Z with the double stroke. Right there. So perfect. Perfect. And then of course, that is N is even. N is an odd integer. N is odd. If and only if. N is equal to what?
2k plus 1.
2k plus 1. Somebody might say 2k minus 1. But I definitely want 2k plus 1 because I want to have a remainder of 1 when I divide by 2. Can you see what I'm saying? If I write it as 2k minus 1, still works, but it doesn't satisfy the language of a remainder. The remainder that we had in second grade when we divided an odd number divided by 2. Right there. So here comes is equal to N equals to 2k plus 1. For some k in Z. Every time I write for some k in Z, I can make it shorter like that. Put a comma, k in Z. Let me circle those two. So once that we have two definitions, I'll circle that one. Right there. Let me circle the other one. Right there, we can start playing. We can start doing some proofs. Right, those two. What else do I need? I need an axiom. Right there. The axiom that I need is that the set of integers have closure under addition and multiplication. The set of integers, Z, has closure under addition, under the operation addition, and products, and multiplication. I don't need to write it really that it also has under multiplication, because multiplication is just like adding many times. So if it has closure under addition, definitely will have closure under multiplication in this equation. But it's nice to say. It's nice to say it for both, right there. Just to make it, yeah. But in principle, you can say, well, no, you only need addition, right there, because multiplying is like adding faster, right there. Okay with that? Perfect. So, by closure, let me tell you what I mean by closure. Take an integer, k, plus take an integer p, that's also an integer. An integer plus an integer is also an integer. That's what we mean by closure. The answer, it's in the set of integers also. So let me say that's by closure we mean if k and q are elements of z, comma, then the sum k plus q is also an element of z. That's what we mean by closure. Not every operation has closure. For example, do you think the integers have closure under division? Do the integers have closure under division?
No.
No. So if you say no, you need to give me the counterexample. Give me a situation where it fails.
3 divided by 2.
Oh, I can hear you. Let me put. I can hear you. My volume is really, really low. You were whispering. Go for it. Go for it.
3 divided by 2.
3 divided by 2. Perfect. That 3 divided by 2. 3 is an integer. 2 is an integer. But 3 divided by 2 is a rational number. It's not an integer. It's not in the set of integers. In Spanish, integers are enteros. Enteros. It's not an integer. So perfect. So yes. And we are not talking about subtraction. We are not talking about subtracting, but that's just like addition. Because if you give me 3 and if you give me minus 2, well, that is addition. Subtract, I'm sorry. If you want me to subtract, and if you want me to do 3 minus 2, 3 minus 2 is 3 plus negative 2. So basically subtraction doesn't exist. It's at the negative right there. Okay with that? So it's addition. So subtraction is addition. And of course, it doesn't have closure under division. Okay, so perfect. Now that we have that, we can start proving something. Here it comes, our first proof from chapter 4. Our first example is example 1. So we have enough math to start doing proofs. If n is an odd integer, comma, then here comes the conclusion. 3n plus 7 is an even integer. There. And it says here we say prove the result. Show the statement is true. Show the conditional statement below is true. Right there. So right away, we must assume the hypothesis. For all, and then that's the hypothesis, and we need to arrive by using definitions and by using algebra. We need to arrive to the conclusion right there. Okay, and it's a formal proof. They need to be complete sentences. We are not writing any symbols. All of it is English complete sentences right there. That's what they want in this class across everybody that teaches this creed right there. So that's it, complete sentences right there. So here we go. Not like we did it in high school in the 60s, in the 70s, in the 80s, that there were reasons and statements in geometry. No way, it's not that. Okay with that. So here it comes, proof. So there I'm saying that I'm starting the proof. PF. Assume an odd integer. Period. I have my first complete sentence right there. I will finish this proof maybe in 4 complete sentences and some algebra right there. So perfect, I have that. So now, as soon as I say that, I need to bring a definition. The definition is going to bring some equations, and the equations will give me algebra to work with right there. And then I will be able to prove it. So then I will say, okay, by definition, I'm using that definition that I just wrote. So I'm going to say it's odd. So by definition, comma, n is equal to 2q plus 1. 2q plus 1 for some q in the integers. For some q in z. Right there. That is another complete sentence. It has a few symbols, and I could have written for some q, and it's for some. It's not for all. It's for some. There is the existence of some q that will just give me n right there. Perfect. So I'm not saying for all of it. It doesn't work for all of them. It's not a dictator, that n. It's just an existential. That q is existential. So I could have written this. I'm going to erase it, but I could have written this. Let me put it in brackets. By definition, there exists q in z such that n is equal to 2q plus 1. So I could have written that. I'm just stressing the for some. For some is existential, right there. And the for some is there. You don't see it. But there is a for some that is omnipresent. Okay, well, I'm telling you how this works. So that for some is omnipresent right there. The test 2 is going to have proofs that you need to write complete sentences on all of them, and the sentences must follow right there. So that's the practice that you need for test 2, but you have plenty of time to conquer this right there. So you worry later. Just pass test 1, and then we'll worry about test 2, but we'll do plenty of practice. The most important topic of this class is proofs right there. So perfect. So, yeah, go for it, Ashley.
Is it okay for us to write for some q as an element of z, or is that wrong?
No, perfect. Write for some. The problem is sometimes math people are lazy and they don't write that. Okay, with that right there. I'm not saying all math people are lazy. It wasn't a universal. But they tend to take shortcuts. And that's a shortcut. So definitely write for some. Perfect. So next, what I'm going to say next is right there. Now, let me go here, a key aspect right here, what comes next. You need, many times, potentially, you're going to feel that lost. What should I do next? You need to bring this in. You need to bring that expression in. You need to bring it into the proof, right there. You cannot say 3n plus 7 is even. You cannot say that in the proof because that's what you need to show. So you cannot assume what you need to show. So bring the expression down. Many times I write this. Take a look at. Take a look at 3n plus 7. Take a look at the expression 3n plus 7. But one of my students in the year 2012, he said at Northridge, he said, it looks more elegant to say, instead of take a look at it, say, consider 3n plus 7. So, since he said consider, I was like, okay, I'll use consider from then on. So, do not consider everything. 3n plus 7 is even, because it sounds like assume 3n plus 7 is even, and you cannot assume the conclusion. So, bring only the expression. So, consider, but only the expression. It's a very short sentence. Consider And now that I'm doing this, consider the expression, because it's not an equation, doesn't have an equal sign. Consider the expression. I never wrote the expression, but it sounds cool to say that. The expression and now you write it down. 3n plus 7. That's a complete sentence. I always write consider 3n plus 7, but consider the expression 3n plus 7 sounds better. It's a longer sentence, it's slightly longer. We are not after being cutting corners and being super short in our proofs. A longer proof we don't mind, unless you made it too long and you are just boring. A proof is a social thing, so you make it for your audience. But these proofs, we can put all the details right here. Consider the expression 3n plus 7. And now comes the algebra. By plugging an algebra, we get, and here we go, because we're going to take the 3n plus 7. We know 3n plus 7 is odd. Well, n is odd, meaning n is odd. Right there. And then we're going to do the algebraic manipulation. So every proof has algebra. Can you see all the algebraic manipulations? Because ultimately I make it look like 2 times something. Can you see? The expression 3n plus 7 became 2 times 3q plus 5. Then I need to convince you that 3q plus 5 is an integer. Use the axiom. I need to use the axiom right now, but I'm almost done. I'm almost done. My goal was to write 3x plus 7, 3n plus 7 as 2 times a sausage. And the sausage is this. Right there. That sausage right there. Students don't want me to call it sausage anymore. Last semester, one of my students said, don't call it sausage, call it little cloud. So I'm going to call it little cloud. So 2 times a little cloud, but that little cloud better be an integer. And it is an integer because q is an integer. Okay with that? So I'll call it the little cloud. Right there. But that little cloud, I'm going to say it. Now the next step is, see that q is an integer. So 3q plus 5 must be an integer because the integers have closure under multiplication and addition. So that 3q plus 5 is an integer. Okay with that? It started with q being an integer. But let me say it. I need to express that. So see that? 3q plus 5 is in Z because the set of integers, because Z has closure. The set Z, the set better, the set of integers, which is Z, has closure under sums and products and multiplication. There. So we were able to write 3n plus 7 as an integer. 2 times an integer, right there, as an even integer. Does, so I'm done. Does 3n plus 7 is even as desired. And then put a little black box, a little black square, telling everybody that you're done. You're done with your argument. You're done with your argument right there. So when I see math majors at UT, this is what they're doing at the blackboard. They're doing proofs. They're doing proofs at every blackboard right there. Now they're going to have a lounge in the 7th floor of the PMA building at UT for math majors, undergrads. So they're going to be doing proofs right there and have coffee. And we have plenty of places at ACC where the computer science majors and the math majors are doing proofs, but there are a lot more computer science majors than math majors. Happiness with that? Perfect, perfect. Math is really popular. At ACC, all the math classes are packed. And at UT, all the math classes are packed. No room for any more classes right there. They're all full. Happiness, and I think it's because of artificial intelligence and machine learning. A lot of students are doing a lot of applied math. So, perfect. Happiness with that, meaning happiness for me. Yeah, I love it. That's going on. Yeah. So, perfect. So, that's it. Can you see what I did? Let me put another example. Let me put another example right away. Right there. Let's go for another one at once. Right there. I can look for one in Susana's right there. Well, let me go for this one. Right away. Example 2. Right away. There. This was example 1. Perfect.
I have a question about example 1. Sorry.
My pleasure.
Why is it that you had to say by definition n equals 2q plus 1, but you didn't have to specify the definition of even integers?
I could have. I could have said recall that the definition of and then I definitely could have done that, Anthony. That's it. But it's very important to do it on the hypothesis because I'm starting the proof. But when I'm coming to the end, here I could have put a line. Let me put it right here. Right here I would have said it. Right when I finish the algebra. Right there. It's not accustomed to do that, but you can definitely do it right here.
Is it required to include the definition of the odd integer?
No, when you finish the odd, yes. Here at the top, you need to start the proof, and that one is required. There, that definition. I'm starting by that definition is important because I'm massaging the hypothesis. But when I'm trying to converge right now to the conclusion, I'm assuming that you already know the definition of an even integer. But of course, it depends on my audience. And then I would have put here recall. As soon as I finish the algebra, I could have said recall that an even integer has the form, the algebraic form, two times k for some k integer is equal to, recall that an even integer is equal to an even integer in brackets I could have done that. No problem. No problem. Right there. Thank you for the question. It's not accustomed to do that, but it's perfect. It depends on the audience. That one. But the definition at the top, it has to be there. Happiness with that, Ansley? Perfect. So let me go and put a new example. Example 2. Let X, B, and Z, comma, or period, comma, or period. I'll put period. If 5x minus 7 is even, comma, then x is odd. Right there. That's example 2. As soon as they write the let means for all. Always. The let on the front like that. And then, so this let means for all. So I could have written for all x's in Z. Can you see that we're in the presence of a universal conditional? And that was in section 3.2. So we have the hypothesis. Let me circle the hypothesis in yellow. All of that is the hypothesis. And we have the conclusion. I'm going to circle the conclusion in green. Right there. So, in principle, we want to go from the hypothesis to the conclusion. Happiness with that. Now, this is impossible to be accomplished right now in the way that statement is written, because algebraically, the hypothesis looks more complicated than the conclusion. Can you see? 5x minus 7, of course, they're both linear. But 5x minus 7 is more complicated than x, right there. So you need, what would you use as your tool to prove this? Let me tell you, you need to swap them. I need a conditional statement that is equivalent to this one and reverse it. Go for it, go for it.
Is it the contrapositive?
You bet. We're going to use the contrapositive. Every single time, the hypothesis has a more complicated structure, algebraic structure, than the conclusion. The contrapositive comes to the rescue. So that is the tool in the back of the mathematician. She has it in her back pocket, like a carpenter. She has the contrapositive in her back pocket. So let's bring the contrapositive. P implies Q is logically equivalent to not Q implies not P. Right there. So this will be a proof by contraposition. The mathematicians will think of this as a direct proof, just like the one that I did before. So somebody in math will think of example 2 and example 1 as the same. But because we're taking this class, and this class is our first class in proofs, we are going to think of this as a proof by contrapositive. And we'll say this is a proof by contrapositive. Right. Can you see what I'm saying? The math people try to dilute it and say it's the same because they are equivalent, those two. It is, but we want to stress it that it's a proof by contrapositive. So I will say, I will write here proof, and I will write by contrapositive. right there. I'll write by contrapositive. And even right there, right under it, I will write the contrapositive in brackets. Right there, I will say this is if x is even, comma, then x 5x minus 7 is odd. Right there. Can you see? I wrote it right under, right there. But of course, when you take your next math class, your professor doesn't need to tell you that she's going by contrapositive. You realize, because she will assume x is even. She'll start the proof assuming that x is even. So you're like, as soon as you realize, you realize that she pulled the contrapositive on you. And then she doesn't have to have any neon lights right there. Can you see what I'm saying? That's in your next math class. On this one, we're perfectly happy to put it on neon lights that we're using the contrapositive. And here we go. We're going to say assume x is in Z and x is even. Or I could have said, assume x is an even integer. I could have said that too. Right there. And period. Right there. Happiness with that. I'm making this very structured. So what's going to be the next sentence that I'm going to write with probability 1?
X equals 2q.
Yes, I'm going to write by definition. I'm going to write by definition. Okay with that? Because yes, I want to write the definition of an even integer. Yes, I agree with Francis. Perfect. I'm going to say, since I can say this, because I can be repetitive. Because x is even, comma, by definition, we have that x is equal to 2k for some k in Z. Perfect. So can you see how we are applying sentences to mathematics right there? And this is a lot of my classmates started math because they hated writing. They hated English. No, we are using more English in math than in English right there. Okay with that, we're constantly using English in math right there because we need to just write this with complete sentences. So perfect. That's it. Once we have that, what am I going to do next? With probability 1, what am I going to say?
5x minus 7 equals 10k plus minus 7.
Oh, okay, but it has to be a complete sentence, Francis. You have to start with consider. Yeah. It's not only equations. You need to make a flow.
So consider 5x minus the expression 5x minus 7.
Perfect. Yes. Consider the expression 5x minus 7. Perfect. You know what I can write next? That is very useful many times. Because we were talking like this, I can actually remind you, at any moment, I can remind you of what I want to show. Because Ansley wanted the definition of, she wanted the definition of odd. Maybe she wants the definition of odd. Remember, you wanted that definition at that moment, at the end, for the conclusion. So we can say that. We can say this. We want to show, or to show, or we want to show 5x minus 7 is an odd integer. Right there. So you're reminding the audience what you're trying to conquer, what you're going to get to, right there. Okay, with that, that always helps. That always helps. And Susana sometimes put those in brackets, but we don't need to put it in brackets. And then the next sentence could be that you remind them of the definition, but you don't have to. You don't have to remind them of the definition, but suppose you want to, put it in brackets. Y is odd if and only if y is equal to 2q plus 1 for some q in z. You have to write there for some q in z, meaning the q in z. You have to. I cannot write that and stop. I author a new variable. I need to tell you where that variable is coming from. Right there. Always. Always. Perfect. Now, that's it. What Francis wanted, we jump onto the algebra right now. We jump onto the algebra. Because we are going to say by algebra, by plugging an algebra, we get and then we start 5x minus 7 is equal to, and then you're going to plug in the 2k. You're going to plug in the 2k. X is even, so you need to use the hypothesis. Right there. And now you need to massage this and make it look odd. Make it look like, when I say make it look odd, is make it look like an odd integer. Massage this algebraically. I let you massage it, and then I'll go and massage it. And at any moment, if you have a question, go for it. I'm having a blast hanging out with you guys. So, the heart of the proof is right here, right now. What we're doing right now. All the other things were the preparations to get to this. This is the heart of the proof, but I cannot write only this. Does not constitute a proof. I have to write all the other verbose stuff. It needs to feel like a computer programming. Back in the 60s, they realized that when they write code, it's very similar than when they write proofs. Here comes the massage. Many different ways I can do it, but I need to get to 2 times a little cloud plus 1. Algebraically, that's my goal. I need to get to that. Okay with that? So I will get to that right now. 10k plus 7 minus 7 right there. It's equal to 10k minus 8 plus 1. Okay with that? Can you see the little trick? So, yes, there is trickeration in proofs. I had to do that. And now you know the story. Factor that too, and I got the little cloud. The little cloud is 5k minus 4. Right there. That little cloud better be an integer. Now I'm fighting. This is an intellectual fight. Now I'm fighting for the 4k minus 4. I need to convince you that, yes, it's an integer. If I don't convince you that 5k minus 4 is an integer, I'm not done. I need to mention something about that. So, perfect. Here it comes. Since Z has closure, the pen is running out. But I'll get the other pen. I have it right next to me. Perfect. So, since Z has closure under addition and products, multiplication, comma, 5k minus 4, it's an element of Z. Right. Can you see that I wrote it slightly different, but it means the same thing. And then I'll say, hence, 5x minus 7 is an odd integer. As desired. Box. And then right there. Any questions on that one? Okay, one more example, but if you have a question, go for it. But again, let me read it if it makes sense. There, so we went by contrapositive. So we swap and negate. So can you see how useful it was chapter 2? Right there. And of course, chapter 3, because this is a universal conditional. So right there, let me remind you of that. I'll write it just. When we have for all x's, in some set D, if P of X, uppercase P of X, then Q of X. The contrapositive, this is for test 1, is for all x's in the domain D, in the set D, comma, if not Q X, then not P X, for those open sentences, open sentences, predicates, right there. So P and Q are open sentences, are predicates. But of course, both with the quantifiers, they are statements with the quantifier on the front. Happiness with that. That's just to practice that definition. That was in section 3.2. Perfect. So let's do another one. Here it comes. Example 3. There. So I'll write it, but I'll dissect it. I'll dissect it all, but I'll write it first. So here it comes. For all x's in Z, let x be in Z, comma, then (11x minus 7) is even if and only if right there x is odd. X is odd right there. This is an if and only if, a two-way avenue. Let me write it with symbols first, and then we'll prove it all. We'll prove it all. So it's a B conditional. B conditional. The symbols look like this. For all x's in some domain, comma, P of x, double arrow, Q of x. So there are two proofs in one. Two proofs in one. On one of them, you're going to assume P of x, and we're going to show that Q, you land on Q. On the other part, you're going to say conversely, you are going to assume Q of x, and you are going to prove P. It's a double whammy. Okay with that? Perfect. Yeah. I don't eat burgers that much. I don't go to get fast food all the time, but it looks like a double days. The double days is you have to go in both directions on this one. Okay, with the double days is a burger at Wendy's. Right there. Okay with that? So it's double the work right there, this one. Happiness. Okay. We go for it. We go for it. Yeah. There. Just let me talk a little bit about it right here, because suppose I come right here, prove, of course, assume x is in Z. That's the first sentence. Assume x is in Z. Now, I want to tell you that I want to prove the if part. If. Somebody might say, show the if part first. Show the if part first. Let me tell you what is the if part. Let me see. I'll go right here. Open this. There. And I open one of these like that. Let me see. There. I'll get a white right there. And I come right here. The if part is this. Because you have P if and only if Q. So you really have P if Q, and you have P only if Q. You have those two. Oh, sorry, went away. You have those two. One of them is that one. And the other one is that one. So the if part, you are going to assume x is odd. You need to assume this one for the if part, the one that is at the end, right there, because P if Q is if Q then P. So So this gets a little bit convoluted, but this is the sketch that we need. I will copy and paste it to our notes at the end. So you need to assume this first. And that means that you're going in that direction. Right there. Assuming the tail, assuming x is odd, and then showing that 11x minus 7 is even. So then you can say that to show comma if to show, I'll write it. With brackets like that. Okay with that? Because it gets confusing when you are doing an if and only if. Right there. So the if part is start at the tail and move in the other direction. Right there. And of course, let me say it on that thing there that I have right here. Anytime right here, sometimes I put it here in the corner. You might have statements that look like this. Oh, I'll go back. There. They might say P if Q. That statement is identical to if Q, then P. Right there. Those are equivalent. Right there. So perfect. So we're here, and that's it. So we'll start with let x be odd, be an odd integer. Comma. By definition, x is equal to 2L plus 1 for some L in Z. Right there. Okay, with that happiness, we use L, we use Q, we use K. Those are very popular. Perfect. Now the next move is going to be consider the expression and the expression is 11x minus 7. Right there. And then we will say by plugging an algebra comma and then we'll go for it. 11x minus 7 we assume was an odd integer, 12 plus 1. Minus 7. And then algebraically, we need to move all of this to make it look like an even integer. 2 times a little cloud, right there. So no problem. 22 L plus 11 minus 7. 22L. 11 minus 7.
4.
Gracias. Perfect. Then factor the 2. So put it right here. You want to make it look like 2 times a little cloud. There. So right here comes, we're almost done. There is the 2. The 11L plus 2. I'll repeat it here, no problem. 11L plus 2 with the brackets right there. So we are almost finished with the if part. I need to say something about the closure. I need to say something about the closure. Happiness with all the moves.
What are the rules for putting brackets?
No major right there. That I can put, what's the question, Brendan? I can put those brackets, squarey brackets like that. Yeah.
Oh, okay.
Well, why? Because you're thinking programming that makes you nervous?
No, I was confused whether those brackets were necessary or whether like that.
No. I tried to make it differently. I could have put them like that too. I can put the regular brackets right there. Yeah. And I can even erase all of this. But the idea is that I wanted to make it look like visually. Let me see. I want to take the little cloud very seriously because it's right there. So it's the 2. Let me put it right there. That's just to show when we study right there. And then right there, I want to have in there the 11L plus 2. Just stressing that right there. But it's my freedom to use the square brackets or the, is that okay? Because I'm not talking about intervals. Intervals, my lower lip trembles because I need to make sure it's a closed interval or an open interval. But here, I'm more relaxed. So, perfect. And now some closure talk. Since Z has closure under addition and multiplication, comma, we get that we get that 11L plus 2 is an element of Z. Thus, 11x minus 7 is even. Right there. Happiness with that. This is an if and only if. I finish with the if portion. And I should put a box, a little squarey bracket, a little black square, but we cannot do that. We're not done with the entire argument. But I need whoever is reading this proof to tell them that I'm done with the if part. So you can use conversely. At the moment that you use conversely, that means that you are applying the converse, that you're going in the other direction. So you can use conversely. Let me tell you all the things that you can use. You can use conversely. Comma, and they know you're done and you're going in the other direction. You can show an arrow that goes in the other direction because we just showed that we had an arrow to the left. So you might say, look, an arrow to the right. Because I'm doing the other direction. But you just proved the if. So you can also say that you are proving the only if right now. So I gave you the 3. You don't need to use the 3 of them. Only one of them suffices right there. So you can use the arrow. You can use only if. or you can use conversely. Anything to tell the reader that you're done and you're going in the other direction. Happiness with that. Look what happens now. I need to apply, I need to go conversely. I need to do the only if part. The only if part is starting here. The only if part is assuming this. And ending with this. Right there. It's going in the other direction. We assume x was odd. And we show that 11x minus 7 is even. Now we need to go in the other direction. Show that 11x minus 7 is even. Meaning, assume that 11x minus 7 is even and show that x must be odd. Happiness. But then you know that I need to use the contrapositive on this one. Because 11x minus 7 is even, is more complicated algebraically than x is odd. Can you see that this is not trivial? Nothing of this is trivial. We practice this because it's not. We need to write complete sentences. So perfect. I will say conversely, and then comma, by contrapositive. We must show that if, and now let's do the contrapositive, we must show that if x is even, 11x minus 7 is odd. Okay, with that on the fly, we're putting the contrapositive right now. So x is even, 11x minus 7 is odd. So if perfect. We have it and we can start. So really fast, I'll finish it. So we're assuming 11x, x is even. So by definition, assume x is even, comma, by definition, x is equal to 2k for some k in Z. Consider the expression (11x minus 7) by algebra, by plugging an algebra. We get undo the algebra. 11x minus 7 equal to 11 times 2k minus 7. Right there. Then 11, well, 22. $22k minus 7. $22k minus 8 plus 1. 2. 11k minus 4. Plus 1. Recall that Z has closure. Under the operations addition and product and multiplication. Let me see multiplication. There. Thus, $11k minus 4 is an integer, and 11x minus 7 is odd. Is an odd integer. As desired. So we are done with the double days right there. A little box. Done. It was double the effort. Right there with a contrapositive in between. Sometimes one direction has the contrapositive. We're going to see in the future that one direction might have the contrapositive. The other direction might have to be, we have to use contradiction. Right there. So sometimes, or it could change the method of proof. Right there when you go from one direction to the other one. One direction could be trivial. You still need to write a proof. But the other direction could be really hard, like in the ninth circle of Dante, right there. That's math. Doesn't have to explain why one direction is more difficult than the other one. Okay with that? Perfect. We're entering a new skill, writing proofs till the end of the semester. But again, worry more about test 1, and then we'll start doing a lot of proofs every class after test 1. Any questions? Any questions? Super freedom, total freedom.
Like if this was LeBron in the Mahomes spot, we'd already be getting the leaks about he needs more help. They didn't find him anyone this year. When Rashee Rice went out, they could have done this, that, and the other thing. They knew Kelsey was getting old. They've got to do more. He took less money. They basically make him a victim.
Wait, I thought
don't
you
think
said he was secretly injured. When you said LeBron, I thought I had a secret injury.
Well, that would be another one too. Yeah, he had like a quad injury. He couldn't push off his right foot. Yeah, they'd be doing all that stuff. But it kind of doesn't seem like Mahomes. Not only does he not do that stuff, but he always seems at peace, win or lose, after the game, right?
Are we sure there's not lingering bitterness with KD for the Achilles injury? Maybe how that was handled by the team.
People don't remember this, Bill. That's why you're Bill Simmons.
I'm not Bill Simmons. I'm Conspiracy Bill. Conspiracy Bill is here.
But that's why.
I'm just asking. I have no inside information. Please don't aggregate this. I just always thought it was a little weird. He hurt his calf, came back, and blew out his Achilles.
People don't remember, and I was like, at the time, there was a bit of a whisper campaign.
Yep.
Today, I wanted to do a story that doesn't. Number of things. It allows us to cover baseball amid the baseball postseason. Sure. It's the ALCS and the NLCS, both underway this week. But it's also a story about somebody that I consider like just a genuinely good friend. That I am pretty sure you consider the opposite. Hollywood showrunner and comedy legend Mike Schur.
Oh, yeah, he's a legendary coward. He's on like my Mount Rushmore of cowards. He might be number one for me personally.
So for people who don't know this, Cortez, the Minister of Heat Propaganda, Parakeet Cortez, that is his legend. Mike Schur is Levitard shows like Resident, Red Sox, baseball, Celtics, Boston super fan, which explains the antagonism.
I heard he's been an actor, like he's done like a bit part with a beard or something. That's like his claim to fame or something. Or
Yeah, exactly. Just on the most popular television show of all time, maybe The Office. But Mike Schur is also somebody who co-founded a baseball blog, Fire Joe Morgan. It was there to criticize the old school baseball broadcasters and journalists during the mid-2000s by using statistical insights like Moneyball stuff, metrics, math.
I remember the blog as a kid. They did, big important things like fighting Bill Plaschke.
Very important. So Mike Schur went on to do yet more important things. I mentioned The Office. He wrote for The Office. He wrote for The Simpsons. He wrote for Saturday Night Live. He made Parks and Rec, Brooklyn Nine-Nine, The Good Place. He's one of the most prolific, accomplished writers in all of entertainment.
I've literally never heard of any of those shows.
Okay. So the good news for you, in all of your ignorance, is that we're not here to talk about any of those shows in specific, despite their fame and success. Because what I want to talk about is how in 2021, Mike Schur got picked by NBC Universal to birth his passion project. He got hired to reboot Field of Dreams.
That old ass movie. That's cool though.
That old ass movie, which lots of people consider the greatest baseball movie of all time. And he was hired to reboot it as a TV show, also called Field of Dreams, which is kind of like being asked to, recast Kevin Costner and also become Kevin Costner's character at the same time.
If you build it, he will come.
Here's the nerdiest best part to date. Mike Schur went out and built an actual baseball field out of actual cornfield in actual Iowa in real life. He built his own Field of Dreams in the Midwest to film the show, as the movie literally tells Kevin Costner himself to do.
So when is this show supposed to come out?
And here's the thing. Because it's not. So